Yeah. And so at different scales, so the lab observation in 3D here you can see, and the field observation, so pretty much the same thing. So we isolate, and we try with different grain size, for instance. We go with some clay silt, so you have the diameter here below 75, and loess is wind-blown silt. So whatever the grain size, and we can see what the impact of grain size of the density, for instance, of these ice layers. Then we developed another cell because the first cell we needed to open the cell and remove the sediment. So now we developed recently a multi-rings frosty cell. So same thing, we control temperature at the top and the bottom and put a thermal gradient. But then we can remove the rings one by one and get easily the sample. Otherwise, we needed to thaw the contact. So this is how it works in the freezing cabinet within the cold room. And we measure this one also. We added a lot of thermistors. In fact, it's thermocouples. And the previous one, it was not as much, and it was not in contact with the ground. It was 0.5 millimeter on the plastic, and we could see the effect. So we improved with this. And so this is the lenticular cryostructure that you can see in the field. You have the field observations here, and you have the lab observations. So this morning I was really pleased to hear, okay, the cracks and how it works, because I see these cracks forming, and we didn't know exactly why it was forming. So sometimes we have them, but sometimes we have no cracks like that. So by reproducing the cryostructures, for us, it helped us to interpret what we see in the field, the conditions when it was formed, because it was formed like thousands of years ago. It's very difficult to find out what it was. That's a new cell, and today I'm not going to present a lot of results per se. I'm presenting equipment we have. The goal when I came here was to present some things about permafrost, but my personal goal was to bridge the scale between physics and geomorphology. And we need to, for interdisciplinary research, make just a footstep in the discipline of the other. And eventually, I've seen that the scale you're working, maybe we can start explaining some of the processes we observe, and maybe I can give you some, or geomorphologists, some examples of stuff that you could work on that is in nature. So this one is a new one. It's a Chinese researcher in the lab for 2 years. It's the small-scale cryopeg cell. So that's just a plexiglass cell, temperature control at the bottom and the top, and we have a porous stone at the base, so we can have bottom-up freezing, top-down freezing, or two-sided freezing. And it is equipped with thermistors, TDR for humidity, and pore water pressure. So we measure everything like that. The expected scenarios that we have is that by two-sided freezing, like we see in the field, we will be creating a cryopeg. So this is a new project. Cryopegs, you will find it in terrestrial permafrost, following clay deposition. We work with the Alfred Wegener Institute and the Munich Technological University. And our task is to bring them some lab and field data, and they're developing the cryogrid model of permafrost. Now they're putting it with salt in it. So we work, with Sebastian Westermann, who did environmental physics. He's at Oslo now. He's developing the model, and we're feeding him with properties to benchmark the model. This I presented, the physical modeling of the active layer detachment, and our hypothesis is that when you have interannual variability and cooling, you form ice, and if you have rain infiltration, you trigger landslides at periods that we didn't have in the past. So this French physicist has been working on that. So that's his cell, the active layer cell. Very simple box, and we have an heat exchanger at the base to maintain it frozen. And we test various scenarios. So saturated sand, 45-degree angle, nothing happened, it just rains. Then we add here ice lenses, same thing, but then we start to have some detachment like that. And this one is a bit messy. This one is no ice lenses, but rain infiltration. So what we create is just mechanical erosion. And, oh, there's one missing. Okay. This one is, I've been contacted by folks at Paris-Saclay who have a hydraulic channel like that, and they do physical modeling. They have water flow in the flume here on frozen soil, and then we check at which temperature and which flow rate you thaw the permafrost. Then if you increase it, you erode mechanically this sediment that has thawed, and if it's cold enough and slow enough, the flow, you grade permafrost. And these are analogs for things that we observe in the field. So snow melt in the summer that will refreeze on the surface. For instance, here you have a little channel and it will refreeze. So we were able to establish these conditions that we observe in the field. It's accepted in a geomorphology journal. It has application also, this is this big ice patch if you want. This inflow of water will percolate through the snow, refreeze at the base of ice here, and create what we call superimposed ice. You have that also in glaciers. Yeah, so that was this simulation. Whoops. Okay, this one was not placed at the right. It's still the active layer detachment slide, and this was our hypothesis. We have saturated sand. We put ice lenses that have, for instance, grown after a cold period, and we have water infiltration here, and exactly you have retrogressive landslides that occur. And well, this one is not working, but we have the thermal fields measured, the humidity measures, and the next step, we're installing pore water pressure transducer to model that. Here, this is the medium scale cell with thermal exchanger, so it's a wooden box. We have copper here that is linked to the thermal bath. We circulate a cooling fluid. We have water input from the top or from the bottom, excuse me, and then we run some different tests. So this test is pretty interesting. In Canada, you know, the Trump administration mentioned that we should be the 51st state. So the Prime Minister of Canada reacted and shifted some of the fundamental research money to the militaries. Then the militaries contacted us. And they said, for real, we had meetings, a lot of researchers, and they said, okay, if we want to install, and that's not a joke, if we want to install a small nuclear reactor on permafrost, what would it do? Okay, so I calculated the thermal charge and so on. I said, well, you're going to be in trouble. That's going to, and it's thick, as you have seen in the previous courses. So we said, we have a solution for you, maybe. It is called pre-thawing before construction. So we arrive, we thaw the permafrost, we remove the water, then we consolidate. All this we do in the lab, but in the field, we're starting this summer at the field scale. We works with big excavators and stuff like that. And then we refreeze the stuff. So you have a very consolidated slab, ice pour, and that can sustain buildings, for instance, or things like that. And because it will settle, we fit it back with non-frost susceptible material. So this is what we do. We are at the field scale experiment. We are at the small scale experiment. This summer, we're trying it in the field, about half the size of the room. Then we develop numerical model, digital twin, and then we will arrive with design guidelines for engineers and stakeholder engagement. So this is the way we thought of permafrost also is interesting, is by steam. So we have a pipe, we inject steam in it, and then it propagates along the pipe. So we calculate the spacing between pipes that we have to do to thaw the permafrost. We measure temperature, water movement, etc. So for instance, here you have 4 scenarios. Saturated sand, ice at the surface. The blue is ice lands, for instance, and they're thick. Ice at the bottom of the, at depth if you want, and very ice-rich permafrost. So this is the thawing, progressing, and then we know how it will progress, the amount of energy we need to put, and where it will thaw. So where we need to remove the water, because it makes a big mess of mud. And so that's the application for that. So this one is the large-scale complete permafrost simulation system. Also, that was really long to design that. It exists in the lab, but we have never used it fully. So it's open to anybody that has a big project, but you need a very good reason, because it's 6 tons of soil, that saturated soil, when you have that. It is a box like that. We have a water container. You can put water at the surface, or you can have it from the bottom if you want to saturate from the bottom. It is, of course, reinforced by steel, and it is adjustable, so to accommodate if you want the expansion with freezing. And at the bottom, we have heat exchanger. In fact, it goes all the way here. So we control totally the bottom. It's fully insulated, and it's in the cold room already, where we control very well the temperature. And also, it is resting on steel support like that, and we can move it and tilt. So we can create a slope, or we can work in like flat or low-lying slopes. So I am not aware of such a facility anywhere to monitor, to simulate permafrost. But like I said, before going to this scale, we need a good reason, because it's a lot of work. So you need to redo the experiment. You got to remove 6 tons of soil. You got to dry 6 tons of soil. You got to sieve 6 tons of soil. Kind of long.
Need a shovel.
Huh?
Need a shovel.
I need students. we have shovels. Okay, so all this is to show you what we have in the lab. And now I want to present you some opportunities for researchers and students. So recently I submitted a proposal. It worked over 6 years, and now we are applied for another 5 years. It's called a Perma Intern, or SEDNA internship. So this is to have hands-on experience in permafrost science, and it is between 2 labs. And this is not necessarily my lab. So if you guys have, or a prof here, wants to work with another prof somewhere, the student can apply to that and receive up 1 to 3 months of scholarship that covers travel, per diem, accommodation, and so on. And what we want exactly is put labs in communication together. So it's not necessarily, I received a lot of it because I post a different opportunity. We had, and then there is the internship from my lab. So this is a 6-month internship for physical modeling. So I post offers and people can apply. And in 3 years, we had 18 interns that came for 6 months from all these countries. So it's super cool. There's always new students in the lab. They exchange together. So this one, I posted on various forums, and that could be an opportunity for you guys to come and work at our lab. And I'm also scientific co-director of the Center for Northern Studies. We are 170 researchers, 300 graduate students, and there you have the website here. We have master, PhD, postdoc projects, international internship and exchange, and we receive also researchers. Yeah.
Is the first teaching more for undergrads or graduate students?
I prefer no undergrad.
Okay.
No undergrad, and I would prefer postdoc and PhD than master. It depends on the project, I would say. Yeah. So these are the opportunities I wanted to present. And now we'll get back to, where is it? Okay, now back to subsea permafrost. I'm not going to discuss about the terrestrial permafrost, so the cryopegs and the saline permafrost, although it's a big topic right now. It has been not studied a lot until now. I want to talk about the marine permafrost or subsea permafrost. So in the high Arctic, along the coast of Ellesmere and a little bit in Greenland, we have ice shelves. So these are big shelves of ice in the sea, and they are different than Antarctic ice shelves. Antarctic ice shelf is usually a glacier tongue that arrives in the sea and forms this platform. In the Arctic, it's different. So Arctic ice shelves are almost not represented in the literature, and they form differently. And I had this idea that under these ice shelves, we could have subsea permafrost. I'll explain to you why. So I am here on one of these ice shelves. This is a canoe. These are students. So that's one time, very special time, that I crossed a glacier on a canoe. So this cannot be more Canadian. This can't be more Canadian. So far, no studies between the interaction of ice shelves and subsea permafrost. So there we have an international group. The top researchers in subsea permafrost are at the Alfred Wegener Institute. And they work with us on this thing. But like I presented, in, I can't recall the first or the second class, this is not the classic subsea permafrost, you know, sea lowering, permafrost aggradation, and then sea transgression, and then it's buried under. It's really contemporary permafrost aggradation. So the questions is permafrost present under this ice shelf, and is it present beyond in the continental shelf? So continental shelf is the extension of the terrestrial part that goes to a certain depth. Then you have a big talus, and then you go to very deep sea. And this is a PhD project, so the influence of permafrost on the ice shelf and vice versa. And eventually, we'll be working on the response to that, to climate change. You must know that subsea permafrost contain methane ice, caltrate. And this is super concentrated methane. So if subsea permafrost degrades, you have these emissions of methane, and apparently that could be quite a positive feedback to warming. So that's the recent interest for that recently. So this is the current subsea permafrost map of the Arctic. So you can see there's a lot in Siberia, there's a lot in Alaska, etc. But if you look at Canada and the Ellesmere coast, their models show no subsea permafrost at all, except areas where you had a sea transgression a little bit. So I intend to revise that map with the projects we're doing. The site, I showed it before, it's Warrant Island, well, in the Arctic Ocean, so we're at 84 north, and the continental shelf is this part here. So that will be deep, that will be a little bit more shallow here. So this is our spot. So the island, these are ice shelves. They're the characteristic of that is that they're undulated. There's a pattern, and it's regular. I know physicists get excited when there's things like that. And it's still debating why we have these roles. There's various explanations, and mostly is numerical modeling. And then you have the sea ice, you have the multi-year sea ice that is a little bit different than that kind of sea ice, for instance. You have another ice shelf here, and then you have what is called by glaciologists ice rise. So for the French people, dôme de glace. It's like a glacier, it's over ice shelf, but a glacier, to be called a glacier, needs to be moving. So this thing is not moving. When you have an ice shelf, then ice a grade on it. Ice shelves are made of seawater, so it's saline partly. There's some brine in the ice shelf. The ice rise is from snow, compaction, melting, refreezing, so meteoritic freshwater ice. So it makes a two-layer system. The one that I study is 40 to 50 meter thick. So you have 50 meters of sea ice that accumulated over so many years. It's composed of sea ice at the base and, like I said, meteoritic ice on top. And it was formed between 5,500 and 3,000 years ago. This is the period we call the neoglacial. So within the Holocene, we had a colder period, the neoglacial. It's about that period. So you see this in any glacier cores and things like that. You see it in marine cores, etc. And how it was dated, because we were not there, it's pretty interesting. You find some wood that floated on the sea at the end of bay, and their last ages are 3,000. After that, no more wood. No more shells, nothing. So it was sealed from the Arctic Ocean. That's when they started to form. So the ice shelf here impede the water to get into the fjord and stuff like that, and that's how it was dated. The Wardent ice rise will be on top of the ice shelf. You see the ice shelf, and this is the ice rise here in front. And mean elevation of about 30 meters about the topography of the ice shelf. And the maximum depth to the seabed is 60 meters. So that's a thick thing. So the hypothesis we had, and I was discussing that this morning, that when we go to the Arctic, it's 24 hours of light, and it's very strong light. And you get overstimulated, your eyes get overstimulated. And then, and it's documented, psychological fact, you get very hyper. And you have grandiose ideas that comes with it. I'm not joking. And plus you have very difficult to sleep under these conditions. There's always some sun somewhere. So this is how I got this idea. I remember very well. Subsea permafrost should be present under the Wardent ice rise. For an ice rise to form, the ice shelf must be grounded to the bottom of the sea. So seawater can go down to -2 degrees C without freezing because of the salt concentration. At -2 degrees C, you're cryotic, you're below zero, but you don't form ice in the clay or in the sediment of the sea bottom. That's one thing. Then if you ground your ice shelf, reach the sea bottom, then in my hypothesis, it creates a thermal bridge between the atmosphere and the seabed. And ice has a super thermal conductivity. So then what goes through the ice column is in contact with mean annual air temperature minus 18. So then when it reaches the bottom, you have the thermal condition to form an grade ice in the seabed. And then in turn, this subsea permafrost contributes to the mechanical stability of ice shelves. So what we did to go beyond just my grandiose ideas, we said, okay, we're going to test that. We use a GPR, which is a ground-penetrating radar. It's an electromagnetic signal that is sent through the sea. And we use a snowmobile. We tow the GPR. It's linked with the GNSS, so precision coordinates. And then we did 150 kilometers of linear measurements with the continuous GPR. Then I met a very brilliant guy. He's French, actually, but he's at the University of Lausanne. And James Irving is English at Lausanne, and they designed a drone-based GPR. So I invited those researchers to come to the field, and we tested that drone-based GPR. That's a first. It's not commercial. It's a new technique. So with the drone, that was super cool because we can reach areas that might be dangerous, and the edge here, it appears smooth, but I swear it is not smooth. So yeah, can I start? That's the drone.
Donc là, je me fais aller à la main proche de son point de départ. Parce que
you run the drone like that. We program the drone, in fact, and it makes these lines up and down the ice shelf. And it worked very well. We reached the bottom of the ice shelf, and now we know it's grounded. These are the linear kilometers we did with the snowmobile. Yeah, that's a lot of work. That's our setup. So this is the PhD student, Elliot. This is Bastien here. And this is the setup we installed. So we work at about minus 20 at this period. Another French student with us. As you can see, I kind of like the French student. Yeah. So with the GPR, we were able to show that near the island, it's anchored to the island. So you have this bedrock, very good thermal conductivity that transmit or favor heat loss. And then there, definitely, just by the island, we have subsea permafrost, but that's no surprise, really. So these are the GPR profiles, and here you have the rolling topography that we see on the ice shelf. You see something like that here, something like that here. And then we have a different type of ice. This is the meteoritic ice. They have two different speeds that we program in our software to determine the depth. And then this is the sea bottom that you see here, this reflector.
You can collect data without stopping?
Yeah. Usually GPR is by step, but we tweaked it. We worked in a way that now we can have it running continuously. And same thing with the drone. So then this is just one of the profile. So we have freshwater ice and seawater ice here. And then we have the sea bottom, and then the limit between seawater ice and freshwater ice. These are interpolated profiles of the topography under the ice shelf and ice rise, and it's not equal. I was surprised. And I think that must be potentially former glacier-pushed material underneath, but very old stuff. And this is the interface between the two, you have here the meters, the interface between the two type of ice. Then what we did, we calculated the average boundary between these two. So the higher we find it and the lower we find it. So the average, and don't ask me anything please about that, it's not my slide and I have no idea what it represents. So the average is about 8 meters above the sea level. So it means that you have sea ice 8 meters above the sea level. How can it be?
Cryosuction.
Nope. I would have liked that, but no. No, now we're going back to more geology, quaternary, and geomorphology. It is isostatic uplift. Okay, so this ice was frozen to the bottom. Sea ice usually like to form at sea level, right? We agree with that? Yeah. And it was pushed up by 8 meters during isostatic uplift, so after deglaciation. So what we do, we collect pieces of wood, plants, shells on the continent, and we date them. So here we have at some dates here. So you have the dates 8,000 something here. And then this is 0 sea level. So that means that if we arrive at 8.32 meters, this means 1,600 years. Why are we interested by that? I'll skip this one. We have in our mind, okay, the ice shelf and the ice rise are frozen to the bottom. Then we have heat loss to the atmosphere, and it promotes permafrost aggradation there. We want to know if this permafrost contains ice, ice-bearing permafrost, not just something that is below zero cryotic. So we use electrical resistivity tomography. And when we run it, so we need to extend for maybe 500 meters, and then we have a little pole, metallic pole, at every 2 meters where we put the electrodes, and we send the electric signal, and then we can reach about 70 to 80 meters depth. If there is ice, it will be super resistive. If there is no ice, then the current can pass easily through the material. So this is, actually they are now, today, they are on the ice shelf trying to install that. And so that's going to tell us if we have a confirmation finally of ice-bearing permafrost, and next year we're trying passive seismic for that. Then we know the boundaries, we know the geometry, we have a time for formation of the ice rise. We use numerical model, we use current climatic conditions. This summer we're installing a thermistor cable in the ice rise. We monitor temperature for 1 to 2 years. And then we run the numerical model over 1,000 years to see how deep and how wide the permafrost extended in the seabed. So we'll be starting with a 1D model of Over the Wind from the Alfred Wegener Institute. And then we intend to go 3D because we want to see the lateral extent that we have with that. So this is our lab on this little island. This is the type of plane and the crazy pilot we contract. They like to do that stuff. So this project is new. And if someone is interested to do some numerical modeling or get into the physics of things or get into the cryopeg stuff, these are new projects, and I will be very happy to have some friend to work on it because we have a little bit too many projects sometimes. So we need some friends. That's it, and thank you for your attention.